Hello, everyone, and welcome to this wonderful lecture. Today, we are going to discuss on the subject computer architecture, and we're going to discuss on the topic register transfer language. So, my name is Dr. Victor Mokaya from the Department of CIT, Suresh Gyan, Vihar University. Now, what you're going to discuss now is to look at the lecture overview of what you're going to cover. So, this is the objectives that we'll be covering. And the first objective for this lecture, we'll look at the subject objective, that is with respect to the syllabus. We'll also look at the outcomes and the reference books that we will be using we will be using in the course of this study. So that is what we'll be looking at as our first stage. Then the second we'll be looking at is the introduction to register transfer language. So we'll cover on the introduction, we'll define what is register transfer language, what it is, how is it useful, why do we need it, where is it applied. All these things will be discussed so that you have a deeper understanding of exactly what computer architecture entails. Next step, we'll look at register transfer. We'll define what is a transfer, we'll define what is a register, and what type of transfer is this we're talking about. Where does it take place, and what are the components that are used? Next, we'll look at the block and timing diagrams. So we'll look at this timing block. These are two different diagrams that help us to understand how transfer of data across different registers is necessary. Lastly, we'll look at the register transfer symbols and notations. Now, it is very necessary to remember that in this subject, we use symbols and notations. So instead of representing everything word by word, we try to use shorthand method, which is also referred to as symbols. And we also have notations. Notations are what help us to know which direction something is going, what this stands for, and why this one is applied. So we look at the relationship between notations and symbol altogether. Now, the first objective we are going to look at here is on the course syllabus. So the subject syllabus that you're going to look at is this computer architecture. And from it, we're required to have a prerequisite or a prior knowledge on microprocessor and interface. So this one is very necessary, and I believe you covered it in your first year. So having had these prerequisites, the course objective that we'll be looking at, one, this course will provide you the knowledge about computer systems and their basic principles. You will also possess the knowledge to analyze system performance. This is what we'll be looking at. Also, the third objective will be to study on the concepts behind advanced pipelining techniques. We will study on a broader detail what is pipelining and what are some of the concepts that are needed. Next, we'll also cover the current state of the art memory system design. So it is very necessary to understand this, that as time progresses, new technologies and inventions are coming up, and we can only be able to make life better, as we say, machines make work easier by continuing to reinvent. The next objective we cover is to provide the knowledge on structural level parallelism. So we'll look at what is parallelism and also understand how instruction level is applied to it. Lastly, we'll be able to cover and to impart the knowledge on nano programming. So the programming of smaller particles is known as nano programming. Now, this course has 5 units, like any other subject that we've been covering before. And in so doing so, we'll be looking at, in a brief, on what is the content of this syllabus, what are you going to cover. that you get yourself prepared and know that after this unit, this is what will follow next. So this syllabus will be provided to you on the LMS for your kind reference. So each unit takes 7 hours, and each unit has an average mark of total marks of 20. So in the first unit, we'll be covering on register transfer language, while on the second unit, we'll cover on CPU organization. On the third unit, we'll cover on arithmetic algorithms. Fourth unit, we'll cover on microprogrammed control. And lastly, we'll cover on memory organization. Just to remind you, all these 5 units are connected to each other. So there is nothing that you're going to study here that is out of topic. Each and every unit that has been detailed and formulated here is useful for your study and syllabus coverage. So these are the reference books that will be applied for the course of this class and beyond. So first we'll cover on J.P. Hayes, Computer Architecture and Organization by McGraw-Hill Publication. Year of this book is 2012. We'll also be able to cover on second is Huring, Computer System Design and Architecture by Pearson Education. And the book here was published in 2003. The third reference book we'll be covering will be on from William Sterling, Computer System, Computer Organization and Architecture. Lastly, we'll cover on the book from Roberto Narboni, Ingrid Paletti, on the title Advanced Customization in Architecture, year 2012. So these are the 4 reference books we'll be covering and looking at into. Now, what we are going to look at next is the course outcomes. What are the outcomes that you are required to possess at the end of this syllabus on this course? Now, class is also very necessary to understand that while you're studying, it should not just be a requirement to fulfill your educational journey. You should be able to come out with something and transform your mind into the mind of an engineer. So these are the outcomes we'll be covering. So the first one will be to possess the ability to understand the operations of electronic logic elements. Second outcome should be is to understand the organization of a computer system in terms of its main components. So these are very necessary concepts to remember always as we are studying. The third outcome should be to understand the various parts of a system memory hierarchy. Fourth is to have the ability to understand the operations of modern CPUs, including pipelining, memory system, as well as buses. Next is to have the ability to understand the principles of operations on multiprocessor system and parallel programming. Next is to have the ability to design and emulate a single cycle or pipeline CPU by given specifications using hardware descriptive language. Next should be the ability to work in teams to design and implement CPU. And lastly is the ability to write reports and make presentations of computer architecture projects. So all these are the course outcomes that we'll be covering. And I believe that by the end of the last lecture for this subject, you'll have had the ability to possess all these skills that have been outlined. Now, we are going to look at our first unit, and the first unit is on register transfer language. Now, before we dive deeper into the register transfer language, it is equally important to have some basic and basic fundamental introduction to the subject. And on that note, we are going to begin with the digital system. So we understand what is a digital system, and by definition, a digital system is modules constructed from digital components. Digital components refers to registers, control logic, decoders. And these digital components, they perform specific tasks on a system. That is what is a digital system. Now, moving on, we've mentioned the modules. Now, these modules, what they do is that they are interconnected with the common data as well as the control path. Now, that kind of connection is what forms a digital computer. Now, from this digital computer system, we've also mentioned that we have digital components, and these digital components basically they include registers, control, logic, as well as coders. Now, what are registers? Registers are a group of flip-flops that are useful for storing bit information. Now, what are flip-flops? Flip-flops are storage units that you can use, and they consist of binary information, that is zeros as well as ones. Now, registers plus operations performed on them make up what is known as a digital. Now, next we have micro operations. Now, from the word operations, we have micro operations. Now, operations that are executed on data stored in one or more registers is known as micro operations. Now, we have a sequence of micro operations that are basically used to describe any function. So we have several of these micro operations in computer architecture, and each of these micro operations are used for executing different operations on the data that is stored on the registers. Now, having said that, what you're going to look at next is to understand what are these type of micro operations. These micro operations will also be able to understand which ones are they and what do they help in regard to data stored in the registers. Now, whenever we apply these micro operations, the output is one, replace previously stored binary information in a register. I repeat, these micro operations, they replace. That means they feed new information into an existing information, and in the end, they kind of create an update. Second is they transfer binary information to another register. Okay, so they can also transfer binary information to another register. So it is sort of like a communication. One register can feed another with information, and another register can also feed another with information. So some of these micro operations that are being performed, the operations that are being performed on a micro operation include shift, count, clear, and load. Please remember these four examples are not micro operations. These are basically the operations that are being performed by micro operations. Okay. So these are shift, count, clear, and load. Now, whenever we are designing the internal hardware organization of a computer, it is also necessary that we specify how it is going to perform activities. And in that respect, we specify the organization of our internal hardware in the following ways. One, we have to specify the set of registers it contains and their function. Any internal hardware has to specify the registers that it contains and their functions. Okay. Just like in your home, your parent knows how many members reside there and who are working, who are students, and who are the servants. This one is also necessary for an internal hardware system. Also, it has to specify a set of micro-operations performed on the binary information that is stored. In any hardware, what are some of the micro-operations that can be performed? By so doing, you can know what type of data is loaded there based on the type of operations that are being done by micro-operations. Then the third is to specify the control functions that initiate the sequence of micro-operations. Now, we need to have a limit, and this limit or guard is what is used to control information coming in and going out. So whenever we want to communicate, there need to be a guard, just like in the main gate of any university, we require a guard to be there so that it can allow existing members, also register new members that are coming in so that they can be known what they are going to do, or if it is the right time for them to enter into the university, or if they are not required, then what they need to do so that they can be required, they can be accepted. So this is what your internal hardware similarly has to specify. That is the registers, micro operations, and control function. Now, next, we are coming now to our discussion. We've done a basic introduction of what we are going to cover. We've defined what is a digital system, we've defined what is a digital computer system. We've talked of now micro operations. Now we are going to look at what is a register transfer language. So, as the name specifies, we've said a register is a pair of flip-flops that is used to manipulate binary data. Now, that means that register transfer language should be a language that is used to transfer information from one register to another in basic sense, right? Now, in a symbolic notation is also used, okay? So a symbolic notation is used, and its purpose is basically to describe the micro operation transfers among registers. Now, like we mentioned before, what a register transfer language is. So this language uses symbolic notation. Okay, so that means symbols are basically. Now, the next steps that we are going to look at are: one, how to define symbol for various types of micro operations, and to describe the hardware that implements these micro operations. Now, we've mentioned on symbolic notations, symbols. Now, let us first understand what is this register transfer and what are these symbols. Now, computer registers are designed or designated by capital letters. So we use capital letters to refer to registers. So in no situation should you write a register in small letters. Always registers need to be written in caps. So whenever we write these registers, sometimes they can be followed by numericals, that is numbers, and those will denote the function of the register. For example, in this case, R1, R2, R3, and R4 refer to processor register. MAR is just letters, capital letters. So MAR means memory address register. And the function of a memory address register is to hold an address for a memory unit. Next, we have PC. PC refers to program counter register, while IR refers to instruction register. Similarly, SR refers to status register. These are the different symbols that symbols and notations that we use for register. Okay. Now, next we are going to look at an example of a register. Now, the individual flip-flops in an n-bit register are numbered in the sequence of 0 to n minus 1. You'll be asking yourself, why n minus 1? Because when we are saying, for example, this n minus 1 corresponds to the total bits of a register. For example, if we have an 8-bit registers, that means if we are starting from 0, we should count 8 digits. Okay, so let's say 1, 0. This 0 is 1, 2, 3, 4, 5, 6, 7, 8. Okay, so n minus 1 is to just help us to understand that the sequence is from 0, and since it is an 8-bit, we don't. If we put here 8, we'll be having 8 individual bits, which is very wrong. So that is why n, we refer to the number of bits, that is 8-bit or 12 or 16-bit, and that will be now n minus 1. So it will have the last value as 7. And these values or these bits are numbered to from the right position towards the left. So we don't start normal counting like 0 to on ascending order from left to right. We start from 0 on the right hand side, moving to the left. Also, we can represent this, say, register as R1, which means register 1. So these are two different ways that we can be able to represent a register. Got it? Now, let us now see other block diagrams of a register. So other ways of drawing the block diagram of a register is by using a process counter. So process counter is a type of register. And this process counter, what it does is that it keeps these bits that need to be accessed in buffer. That means one bit is being accessed, then the next bit will stay online. Okay, like in the queue, next in line. So in so doing, that is what we do. So in this process counter, we can divide it into two components. That is the lower byte and the higher byte. Lower byte is from 0 to 7, and the upper byte is now from 8 to 15. Now you can see the labeling of these individual bits is still from the right to the left. That is how we do it. Now let us come now to register transform. Now, whenever we are performing register transform, we are transferring information from one register to another. And when we do that, we use something known as a replacement operator. This arrow is what is known as a replacement operator. So what it does, it specifies that information is moving from R1 pointing to the destination. R1 becomes the source, R2 the destination. So this statement denotes a transfer of contents from register 1 into register 2. So this happens in one clock cycle. Okay, so that means at once interval of time, you can be able to send information. So this R1 to R2 cannot happen twice. Okay, I mean, like, you cannot send half the information and then half the information the other. No, within that particular time frame, communication has to be done. There's no unfinished activity here. So the content of R1 here is the source, do not change. Okay, whatever is being processed or stored in R1 does not change, but whatever is stored in R2 will be changed after transfer. Okay, that means when R1 deposits its contents in R2, whatever was previously stored in R2 will be displaced with the new information that is being transferred by R1. Now, for this to take place, some assumptions. We have to assume that there are some things which are relative. There are some conditions which are put in place. we are assuming that the circuits are available and those circuits are connected to each other. That is, R1 is connected to R2, and this destination, that is R2, has a parallel load capability. That means simultaneously this R2 is able to accommodate or can be able to receive information. Okay. Now, sometimes we do have conditional transfer. Situations where we don't have these clock cycles, we can have conditional transfers. And these conditional transfers can only occur when we have a control condition. So this control condition, okay, so what makes it different from the other transfer that we've mentioned before of a clock transfer? Now in the clock transfer, if you can see this diagram, did not have this value, this condition P0 rather. It was just R1 and R2, and we just mentioned we require this transfer takes place within a clock cycle. Now in this case, when we say conditional transfers, we introduce this condition P0. The binary condition P is given by 0 or 1. So that means 0 or 1 should be meaning something. Now, 0 is when this conditional transfer allows R1 to send its information to R2. When P0 turns to P1, it means that now it can be able to restrict any other register that wants to communicate. So it means that at that point, R1 is not able to communicate with R2 whenever P is 1. But when P is 0, then communication can take place. Okay. This means that the content of R1 is transferred onto R2 only if P is 1. Now, the next thing that you're going to look at is register transfer using a hardware implementation of a control transform. Now, P here is the conditional transfer, but we have not specified if it is a 0 or a 1. So what occurs in this case is that now we are going to look at this block diagram as well as a timing diagram. So P, please remember P is the conditional transfer that allows communication to take place. So if P is 0, transfer will not occur, but if it is 1, then transfer is taking place. Now in this block diagram, let's assume that P is equals to 1. That means R1 can now load information, and at the same time, a clock cycle can be introduced. Okay, so this is just a summary of previous concepts we've covered. So we've said R1 can communicate to R2, then we mentioned at only particular clock cycle, and now we said before we have a clock cycle, we need a control transfer, which is now denoted by P. So that means R1 can only pass a certain bit of information to the buffer for transfer. Once it is loaded here, then it can be transferred to R2. The same can be represented using a timing diagram where we have clock cycles. So this clock cycle is so you can see this time is continuous because time does not stop. Time is moving and every time. So you cannot say that at this instance, when transfer is not taken, the curve here will be flat. No, it just shows that time keeps on moving. So we will use a clock cycle and a load cycle. So this load is used to indicate now the loaded information from R1 when P is equals to 1. So before the transfer takes place, the clock cycle is not counted. So we do not count. But the moment data has been loaded, now we start counting the time. So this shift in this rise shows that transfer is occurring. And at this particular instance, the transfer occurs. That means contents of R1 have been sent to R2. So at this time, then what occurs is that P now removes the control. That means P turns to 0 because transfer has taken place and the clock cycle stops. That means R1 cannot communicate again with R2. Now these are the basic symbols for register transfer. This is sort of like a summary of the basic symbols that you can be able to apply for any register transfer. So this table is divided into 3 columns, that is symbol, description, and example. Now let us look at each one of them and understand what particular function they play. Now the first one is symbol. So symbol, we have letters and numerals. So whenever we have letters and numerals, the description of what they stands for is that they represent a register. So registers can either be in capital letters, like we mentioned before, or capital letters and numericals. So first one we have is MAR, which means memory address register, and R2, which means register. Next we have is the parenthesis. So parenthesis stands for part of a register. So it means if it is a part of the register, then there's a register and part of it. In that direction, you can say that R2 into brackets, this bracket at the parenthesis. So the part of R2 that we are talking about is from 8 to 15, which is the upper byte. Or you can represent this R2 with H, which means the higher byte of R2. That is part of a register. Then we have the arrow. Okay, so the arrow or the replacement operator, in this case, denotes transfer of information. So R1 points to where the transfer is going to take place. So transfer of information is moved from R1 to R2. So this arrow is pointing to the destination. Then next, we have the comma. So the comma separates two microoperations. So whenever we are representing several microoperations all together, we can use comma. So this comma will now separate the microoperations that are being formed. Now, an example of the same is R1 is transferring its contents to R2. And then we have another microoperation, that is R2 is loading information into R1. So this is two types of microoperations represented together with separation of a comma. Now we've come to the end of our class for study today, and this lecture has been prepared with the book from Maurice M. Mano, Computer System Architecture. The first edition was in 1992, and now the edition that has been used for this lecture is the 2006 edition. This is not edition rather, but the publication here. Now we'll now cover the MCQs, the questions that we are going to discuss. And the first question is, which operations are used for addition, subtraction, increment, decrement, and complement function. So the operations that are used for addition, subtraction, increment, decrement, complement are all of them. So we can use these arithmetic operations. We can use the memory transfer and the bus for performing all these operations. Next is the method of writing symbols to indicate a provided computational process is known as. So when we use symbols to indicate a computational process, basically that refers to programming. Okay, that is programming language. In a programming language, you have the provisions to indicate a computational process. Next question we look at is in register transfer, the instruction register is, so the instruction register is denoted by IR. IR refers to the instruction. How many types of operations in micro operations are there? So the types of operations in micro operations are as follows. So we have first, we do have the load, we have clear, we also have the micro operation, which is the, sorry, just to begin again, we have 4 types of them, and that is the load, shift, clear, and one more. So there are 4 in number. So next we'll have, sorry, and count. Now, the next question that you're going to have is what RTL stands for. So RTL stands for basically the register transfer language. Next, micro operation is shown as. So in this question, you're supposed to give the correct notation of a micro operation. The micro operation always points from the right towards the left. So that means the option B is the correct. Second question is the symbol parenthesis is used for what purpose? Now, the parenthesis symbol is used to represent part of a register. And in that case, we say that we can do that when we want to represent, say, we have a lower bit and lower byte and a higher byte. So for that case, we can represent it using a parenthesis. Next, we are going to look at question is, what is the purpose of a clock in a register transfer? The purpose of a clock in a register transfer is to, 1, to schedule total transfer time, to prevent other registers from communicating, to coordinate with the control signal, to carry the data being transferred. So the control signal, sorry, the clock here, the purpose of the clock is actually to schedule the total time of transfer. By so doing, we are able to know this transfer is going to take place within this amount of time, and this transfer also take place, stop at this particular time interval. Now, the next question we are going to look at is, what does this mean? PO R2, then we have the replacement operator, R1. So we say that transfer can only take place if P, P is 1. So that means the contents of R2 can only be, the contents of R1 can be transferred to R2 whenever P is 1. Okay. This means that the contents of R2 of R1 can only be transferred into R2 if P is 1. Okay. Next question is, which of the following is not an operation carried out by micro operations? So the operation carried out, which one is not an operation? There are four types of operations. That is the load, count, shift, and clear. In this case, we have arithmetic. Arithmetic is not an operation, but arithmetic is an example of a micro operation. So we've come to the end of this lecture and covered on the fundamentals, introduction, and I will just give a recap. So first of all, we defined on the basic terminology. We started with what is a register. We also mentioned on how we can represent the block diagram of a register. We also talked of what is a micro operation. What are the operations that are being performed by a micro operation? We also looked at how we can be able to represent micro operation. So we talked of how we can use a clock and how we can use a transfer, control transfer. So that using a control condition P, and we say that this can only take place when P is 0, is the 1, that is when transfer can take place. Otherwise, whenever P is 0, transfer cannot take place. So we also discussed on the symbols and notation. We say that one, we use letters and numerals to represent registers. We use parentheses to represent part of a register. And lastly, we say that we can only be able to use a comma whenever we want to represent to separate micro operations. That is what we've been able to cover in this class. And now we are coming to the end of our lecture. I believe that the next coming class we'll be able to understand. If by the end of the next class, we'll be able to have understood what we covered today. So in the next class, we'll also be covering on the same, but now we'll be looking at the different types of micro operations. Also be looking at what is a multiplexer. We'll also look at what is a three-state buffer, different types of micro operations that exist. And by so doing, we'll also be able to see between a multiplexer and a three-state buffer, which one is better. So that is the end of this lecture. And let's meet again in the next coming lecture.